All right, everybody, welcome back here. Lesson 6.3, binomial radical expressions. Okay, today we're going to talk about adding and subtracting radicals. Basically, once you simplify them, they just become like terms. Okay, like radicals are radicals that have the same index. Okay, so you have to do square roots with square roots, cube roots with cube roots, etc., and the same radicand. Okay, so root 7s with other root 7s, root 2s with other root 2s. So you see here, our first example, we have two cube roots of 7 plus 3 cube roots of 7. So how many cube roots of 7 do you have? Okay, this is all like, all right, and that allows us to be able to combine them. So 2 plus 3 is 5 cube roots of 7. All right, you also encounter situations where things might combine if you simplify them. So let's see what we got here. We got a more challenging question here. We're dealing with the fourth root. Okay, so we have to practice our fourth powers. All right, so we have 4 times, if we split up the fourth root of 32, that goes into the 16 and 2. The fourth root of 16 is 2. So this term actually turns into 8 times the fourth root of 2. Okay, and then we do the same thing with the fourth root of 162. Okay, look at your powers of 162. Okay, your factors of 162, and we have an 81 in there. Fourth root of 81 is 3. And that becomes 6 times the fourth root of 2. So when we look to combine these, I have how many fourth roots of 2 plus how many fourth roots of 2? 8 plus 6 is 14 fourth roots of 2. Okay, so if you go to add or subtract these, make sure you're doing it with like terms. Okay, just like it says up here. Okay, we've been doing combining like terms since pre-algebra, so it's no different now. We have the radicals, same index, same radicand. Okay, multiplying radicals. Once again, our rules don't change. Okay, just what's inside there changes. So we still are going to FOIL these two binomials. So 2 times 3 is 6. 2 times 2 root 3 is 4 root 3. Negative root 5 times 3 is negative 3 root 5. And then negative root 5 times 2 root 3. Okay, remember, multiply the outsides together. So negative 1 times 2 is negative 2. Multiply the insides together. 5 times 3 is 15. Okay, as we look at this, okay, I can't simplify anything else because there's no perfect squares hiding within a 3, a 5, or a 15. We don't have any like terms. Okay, so this is actually going to be our final answer. All right. The next one, okay, this is that common mistake we've been talking about over the last couple of days. Okay, what does it mean to square something? Okay. To square something means to multiply it by itself. The squared does not distribute over addition or subtraction. So that's a no-no. All right, so we're going to multiply root 3 plus root 7 times itself. And then we FOIL. So root 3 times root 3, okay, is root 9. Root 3 times 7 is root 21. Root 7 times root 3, another root 21. And then root 7 times root 7 is root 49. Okay. Now I recognize some of you might be like, why did you do root 3 times root 3 is 9? Okay. Root 3 times root 3 is root 3 squared. Square and a square root cancel. A 3 is going to pop out. Some of you can do that in your head and process that. All right. I just showed you, going back to some of the properties, you just multiply it with the radicands together and then simplify later. So root 9, yes, will turn to 3. Okay, root 21 plus root 21 is 2 root 21s. Okay, and then square root of 49 is 7, so your final answer is 10 plus 2 root 21. Okay, moving forward, rationalizing binomial radicals. Okay, we're going to connect this idea to something we've done in chapter 4. Okay, to rationalize the denominator with a binomial radical, you must multiply the numerator and the denominator by the conjugate of the denominator. Where else did we hear that term of conjugate? Yes, complex numbers. Okay, we multiply by the complex conjugate. All right, so there's no other way to get rid of that root 5 down there other than to multiply by the conjugate. Okay, so what is the conjugate? Remember, everything stays the same. We just change the sign in the middle. So it's subtraction, so now I'm going to make it addition. All right, so that's technically a giant 1. So multiplying by 1 doesn't change the value of my equation. Now all we do is FOIL it out and then see what simplifies, if anything. So let's do my numerator first. Okay, so 3 plus 3 root 5 minus root 2 minus root 10. Nothing I can do to simplify any of that. In my denominator, watch what happens. I should no longer have a radical down there. So 1 times 1 is 1. 1 times root 5 is positive root 5. Negative root 5 times 1 is negative root 5. And then negative root 5 times root 5 is negative root 25. Most of you can say negative 5 there. That's fine. Okay, so my numerator doesn't change. Notice, just like imaginary numbers, our I disappeared. We were trying to get I to go away. Now we're trying to get the radical to go away. And the only terms left with radicals disappears because that turns into 1 minus 5, which becomes negative 4. Okay. Sometimes things do combine in the numerator. The larger numbers you have, the more factors. There might be perfect squares in there where you can simplify, combine like terms, and then maybe pull out a greatest common factor to simplify with your denominator. This example did not do that. However, when you get to class and we look at the worksheet, you are going to see some ones that do that. Okay. All right. So continuing on with rationalizing denominator. We've seen these before where here we just, the square root of 3 is down there, so we're going to multiply by root 3 over root 3. So we have 2 root 3, and then root 3 times root 3 is root 9. Okay, I thought we were getting rid of the radical. We are. Root 3 times root 3, square root of 9, square root of 9 is 3. Okay, some of you are going to avoid that root 9 step and just say that it becomes 3. You know that. Okay, so we can use that idea down here in our denominator. Root 3 times root 3 is root 3 squared, and the square and the square root are going to cancel out, and the 3 is going to fall out. All right, so we're going to stick to that idea, okay, and apply it to the next question. Okay, because this is the square root, I only needed to get an exponent of 2. Down here, I'm dealing with the cube root. Okay, so now I need 3 of the same number multiplied together. I need it to be a perfect cubed in order for the cube root to cancel out. So our giant 1 is going to look a little different. Okay, many people are just tempted to multiply by the cube root of 6. Well, that only gives you the cube root of 36, which isn't a perfect cube. Okay, so I'm going to do, I need 6 3 times. All right, because my end goal here is to get the cube root of 6 cubed. All right, that way the cube and the cube root cancel. Cube root, cube cancels, 6 falls out. No more radical down there. Okay, so how can we make that 6 cubed? Well, I already have 6 to the first here, so I need to make this 6 squared to make it a total of 6 cubed. Okay, so there's our giant 1. The cube root of 6 squared. All right, so our numerator is 4 times the cube root. 6 squared is 36. Our denominator turns into the cube root of 6 cubed. Okay, I'm writing this just to show you how it disappears. The cube and the cube root cancel, and just a 6 falls out. All right, this one we can further simplify, not inside the radical, but the fraction, the coefficients out front. 4/6 reduces to 2/3, and then our cube root of 36 is still up there. I don't have any perfect cubes in there. The only ones that would be 8 or 27, and they're not factors of 36. So this would be your final answer. Okay. Okay, let's try one more here. Okay, and this one's a little bit different. Same idea, but there's kind of a little shortcut here if you recognize it. All right. So for me, all right, I've been doing these, and just like the previous problem, I want 3 equal parts up here. You're like 1, and there's 2 more. There's 3 equal parts to satisfy the cube root. Okay, well I have a cube root here, but 49, I can rewrite 49. Can I rewrite 49 as 7 squared? All right, which means I already have 2 equal parts of the 7. All right, so that's going to keep our numbers down. All right, that's going to keep our numbers low and easy to work with, and then save us steps later in the simplification process. Yeah, you could multiply by the cube root of 49 squared, but then you have a very large number down here, and then you're going to have to simplify in the numerator and then simplify more coefficients. Okay, if you're asking me, I'd rather do less work. Okay, so basically my first step here in blue, I just rewrote it. I turned my 49 into 7 squared. Now, my giant 1, I already have 2 7s, so I just need 1 more. All right, so now my denominator is the cube root of 7 cubed, all right, which I know the cube and the cube root are going to cancel. All right. So again, I'm showing every step along the way, just to kind of make it crystal clear for you guys. If you know that this right here gives you this, which you ultimately know is going to, 7's going to pop out, then just put a 7 there. That's fine. All right. But I'm showing this just to show the cube and the cube root canceling, which is how we rationalize the denominator. I turn my irrational denominator into a rational number. Okay, I turn it into an integer. All right, so there's our answer for that guy. All right, that concludes section 6.3. We're going to continue on with 6.4. Okay, this is a pretty simple topic as well, dealing with rational exponents. Rational meaning fractional exponents. How do we handle if our exponent is a fraction? Right. So this is the rule here from our laws of exponents that we're going to deal with. Okay, so we're going to pull this out and kind of dissect. I have a little shortcut that I'm going to show you how you're supposed to know that the x value always goes here and the y value always goes here. These two things are the same. One, the power is just on the inside. The second one, the power is on the outside. They're both equivalent. It doesn't matter which way you put it. Okay, so we'll see some examples of that. All right. So what is a rational number? A rational number is a number that can be written as a fraction. All right. We said that from the introduction of the lesson. All right. So definition of rational exponents. Again, this is out of the textbook. If the nth root of a is a real number and m and n are integers, then you take the nth root of x to the first, which translates to x to the 1 over nth power. All right. Therefore, if we add a power on the outside, okay, this m value, all right, we can rewrite our exponents that way. All right. I like to call this little trick flower power. All right, so I'm going to take this picture here and I'm going to blow it up and make it bigger. Okay, so I'm going to draw a little flower. Okay, I'm by no means any artist. Okay, but we understand the idea here. All right, when we look at this power, okay, this fractional exponent, okay, on the bottom, underneath the ground, this is our fraction bar. Underneath the ground are what? Roots, okay? And then the top, up here's the sun, up here's the rain, it's, all the stuff that makes the plant grow. Okay, that's the power of the plant, all right? So this essentially, this little picture here, this fractional exponent, translates to exactly the parts of our radical. N is whatever root you're taking. Okay, whether it's a 2, it's a square root. N is 3, it's a cube root. That index is 4, it's the fourth root. Okay, so that's the root. Okay, the denominator of our fractional exponent becomes the root. And then m is the power we raise it to. So whether that m is raised underneath the radical, okay, or it's outside, it doesn't matter, they're both equivalent. So it's essentially power over root, all right, and you just think of any plant and the roots under the ground, okay. It's a really quick and easy comparison to know, okay, what's the numerator? Is the numerator here, here? Or is the denominator here, here? The roots are always underground, okay, and the root becomes the index of our radical. Okay, so let's try a couple examples here just to practice going back and forth. All right, so remember that's power over root. So this translates to x, okay, becomes our radicand, the number underneath our radical sign. I'm taking the square root of that and then raising it to the third power. Now, we don't have to technically put a 2 in there as the index if it's just square root, all right? Doesn't matter either way, but most times you're not going to see that there, all right? If those of you who chose to put the power underneath, this is also an acceptable equivalent solution. The second one, y to the negative 3.5. Okay, well, this is y to the negative 3 1/2. I don't want to see my fractional exponent as a mixed number. I need to translate that to an improper fraction. Okay, so we do denominator times the whole number. 2 times 3 is 6, plus 1 is 7, so that's y to the negative 7/2 power. Now I can rewrite that. Okay, your base becomes your radicand. You're taking the square root and raising it to the negative 7th power. All right, or you could do this. Okay, you could take that even further with the laws of exponents, take the reciprocal of the base, make the exponent positive. I'm going to leave it at that for now and just keep plugging away. All right, this next one, the square root of a to the 5th. Okay, so what is your power? Your power out here, if there's no number, is 2. So remember, power, that's your power right there, and 2 is your root. So that's a to the 5/2 power. Make sure that that is raised as an exponent. Some people get lazy and they're like, they do this. Okay, well, does that mean a times 5/2? I don't know what that means. Make it obvious that that is raised. Okay, there should be no question about it. And if you have to put a little caret there, then do it so I know that it is definitely raised as an exponent. All right, let's do another example here. Again, the 3 is the root, 4 is the power, and it's power over root. Okay, so pretty simple there if we use our flower power trick. Now we're going to throw some numbers at you, okay, and see how these simplify, because yeah, what's the point of just rewriting from one form to the next if things aren't going to clean up? Okay, so let's see here. 16 to the 5/4. Okay, so 16 becomes my radicand. I'm doing the 4th root of that. And then, which way does it make sense to put the 5? Do you want the 5 out here? Or do you want the 5 in here? Okay, so it doesn't matter which one's which. However, if I'm simplifying this, I'm doing this without a calculator, would I rather deal with 16 to the 5th power, which I don't know what that is. It's a very large number. Or would I rather deal with the 4th root of 16? That I actually know. The 4th root of 16 is 2. So 2 to the 5th power, I know that 2 times 2 times 2 times 2 times 2, 5 times, is 32. Okay. If I would do it this way, okay, the second option here in green, I would have to know what 16 to the 5th power is and then know that the 4th root of that becomes 32. I don't know that 32 to the 4th power equals that number. All right, so that's why sometimes it's convenient to have it inside, sometimes it's convenient to have it outside. Okay. All right, let's look at the next one. 4 to the negative 2.5 power. All right, so this becomes 4 to the negative 2 1/2, which is 4 to the negative 5/2 power. All right, if I rewrite this with flower power, going back to my radical, I'm taking the square root, remember the root becomes that, the index of 4, and then raising it to the negative 5th power. I know what the square root of 4 is. If I put the negative 5 on the inside, I don't know what 4 to the negative 5th power is in my head mentally. So I'm going to keep it simple. The square root of 4 is 2, and then 2 to the negative fifth. Well, negative powers tell me to take the reciprocal and make the exponent positive, so that just becomes 1 over 32. All right? And all these answers here, okay, we could confirm them on the calculator. You're not going to get any points from going from the problem to the solution unless you have the work here and your knowledge of exponents. But make sure, I'm going to show you this, make sure that you do 5/4 as an exponent. I know with the regular TI 83s, you have to do 16 caret left parenthesis. Okay, this calculator automatically puts the exponent up there, and then you continue to type in it, which kind of makes it nice. So there's checking my first one. 4 raised to the negative 2.5. Okay, I don't, what's that? That's my decimal. Make it a fraction. Hit math, fraction, enter. There's my 1 over 32. However, as you saw, we didn't pick up a calculator once to do these. All right, we did all this work mentally in our head. Okay, let's try this next one. X to the 2/7 times x to the 5/14. We know that when we are multiplying exponents with like bases, what do we do to the exponents? We add them. So I need to add 2/7 plus 5/14. Well, in order to add fractions, I need common denominators. Common denominator is 14. So that becomes 4/14 plus 5/14, which is 9/14. So I have x to the 9/14 power, which now I can take further and say I want the 14th root of x to the 9th power. Okay, and again, it doesn't matter whether that exponent, the power is on the inside or the outside, either one of these. Okay, let's try one more. So we look at this guy here. Here we could distribute this, okay, and say that that's 27 to the 1/3, and then 6 times 1/3 is x squared, and then we can clean this up. That means the cube root of 27 to the first power, which is 3 to the first, or 3, so it's 3x squared. Okay. The other way you could do this is, since you know that 27x to the 6 is all to the 1/3 power, all right, you could take this whole thing as your radicand. Okay, that base goes under your radical symbol. Okay, I'm taking the cube root of that and then raising it to the first power, which really doesn't do anything. So, same thing, you take the cube root of 27, which is 3, and then x to the 6, the cube root of that, well, there's x to the 6th. All right, so how many groups of 3 are in there? There's one group of 3, there's two groups of 3. So my two groups, there's my two groups, x squared. So your answer is 3x squared. Either way, either perspective, you should yield the same solution. Okay, so a couple different things there that we did today. If you have any questions, when we get to class, ask. We'll have an opportunity to practice some of these things. And again, I want to see and hear your guys' perspectives. How did you do it? Did you use laws of exponents and then do your flower power? Did you do flower power first? Okay, there's more than one path to take to solve some of these. And sharing those thoughts and ideas is valuable not only to yourself in learning and explaining, but also to your classmates to understand a different perspective. Okay, we'll see you back in class tomorrow.